All right, so again, good morning, everybody, or good afternoon, from which side of the globe you're in. Today is Wednesday, the 8th of January in 2014. It's 10:30 in the morning from Brisbane in Australia, where I am broadcasting this class. So today's topic, we will be covering all about IPv6. So this first session, we have 4 sessions all throughout the day. The first session, for 1 hour, we'll be covering the basics. We will look at the IPv6 overview. Now, a few housekeeping things before we go into that. A bit of introduction about myself. My name is Cheryl Hermoso. I work as a training officer for APNIC. Now, the APNIC training team do deliver workshops, face-to-face trainings, and tutorials like that to the members of the internet community in the Asia-Pacific region. Now, we also offer these e-learning courses as a substitute for that, for those of you who cannot attend the face-to-face workshops. Now, the topics that we cover are all about the internet-related things, IPv6, of course, internet resource management, network security, DNS, DNSSEC, and also some routing concepts as well. Now, just a reminder that this class will run for 1 hour. You probably already know that by now. And by the end of the class, I will be asking you to fill up a brief survey for me so that we know whether we've achieved our goal in coming into this class, and also if we have other possible topics that you want to be covered in future e-learning courses. Alright, so with that, let's go on ahead and look at what we will be covering. So essentially, this is a basics course. I would assume that somehow you have an idea or you've heard about IPv6 before and are interested to know more. Okay, so nothing more than that. So we will be covering the very basics. What is IPv6? Why do we have IPv6? How come we have IPv4, but we still need IPv6? Things like that. These are common questions that people ask on a day-to-day basis once they've heard about this new protocol. So we'll look at the background of IPv6, how it started, what are the changes from v4 to v6, what are the functional improvements, what are the new features that have been introduced. We will be looking at the header so we can have a better comparison. We will look at the different addressing models because that's very important. Before you actually go on and deploy an IPv6 network, you have to understand the different types of IPv6 addresses as well. Now, in this class, being just an overview, we have a separate module that discusses the IPv6 addresses in more detail, but we will still have a look at that because that is essential as we move on. We will look at two different parts, I would say, of an IPv6 address. Half of that is what we call the interface ID. We'll look at the different types of prefixes, especially the ones that are available to the public, which are called global network prefixes. And then how do we distribute IPv6 addresses? What is the hierarchy? Where do we get them from? Or if we are an ISP, how do we then distribute them further to our customers? So sounds like a very large content that we have here. We'll try to fit in as much as possible in here. If you do have questions at any time, please feel free to do so. I do encourage participation in this class. And also, if you have anything to add, maybe someone sent a question and then you know the answer, or you have something to supplement my answer, then by all means, please do so. Please write them down on the chat window. All right? Okay, so let's go ahead and look at IPv6. Now, the first question is, what is IPv6? Before we go into that, it is also essential that we understand what is a protocol. So what is a protocol? Everybody coming here should know that. A protocol defines the rules for data communication. So they are sort of like a common language that is used by different devices that connects to the internet so that they will have some sort of meaningful communication, meaningful conversation. So protocols achieve this by defining the nature of, let's say, what sort of information is being sent, how to understand these information that they are receiving. So these are just sets of ones and zeros that is coming into them, but how do they interpret them? So we have a protocol stack that groups them together and makes them into different layers. So that essentially defines in a gist what a protocol is. So next is, what is an internet protocol? Okay, IP. What is IP? IP is part of the TCP/IP protocol suite. It is responsible for the delivery of data to the target destination. So you have your source address, you have your destination address. These are logical addresses, right? TCP/IP, I would say, is probably the main language that is used on the internet. So everybody that connects to the internet, most of them, of course, would have to understand this main language. So now we move on and define what is IPv6. So you know IP. Now what is IPv6? IPv6 is of course a version of IP. IPv6, you can say that it is a newer version of the Internet Layer Protocol in the TCP/IP protocol suite. So the goal of IPv6 is, well, it's essentially to replace IPv4, but currently it is to complement the currently existing version of IP, which is IPv4. So you can say that IPv6 is a new protocol, all right? The word new in this case, well, it's being used loosely because technically IPv6, as we will see that later on, IPv6 is really not so new anymore. IPv6 has been around for a while now. It has been established in the 1990s, and the protocol was actually standardized in 1998. So originally, it was meant to replace again the current protocol for interconnecting our networking and host devices. Right? Now, another thing that I commonly get asked is, how come we have to jump from IPv4 to IPv6? So where is IPv5? So actually, there is IPv5. IPv5 is what we call the Internet Stream Protocol. But it was an experimental protocol. It was never implemented. Manufacturers don't exactly have to adhere to this protocol when they come up with new products. So there is IPv5. It has something to do with streaming, so something to do with your video, web streaming, and that kind of stuff. But again, it's not an actual standard. I can see that Mokbul is having problems with his audio. Is anybody else having the same problem? Or is it just him? Okay, it looks like it seems okay for everybody else. Can I know, Mokbul, where you're coming from? Maybe it's got something to do with the bandwidth. I'm not so sure. What I can suggest for now is try to get out of the session and then log back in again. All right. Okay. Let's continue, everyone. Where am I? We've stopped with IPv5. So another thing about IPv6 is when you look at earlier documents, you will not see IPv6 because it wasn't called IPv6 until it was standardized. So most of the early conversations in the mailing lists, most of the early documents actually describe something called IPNG, or the IP next generation. So as you can see, there is an idea there that this is a next generation of IP that will replace IP version 4. So this is the TCP protocol suite, TCP/IP protocol suite. I just want to show you where we're working on. Most of the changes that will happen when you move from v4 to v6 is of course confined in this layer. This is the layer that contains your IP. However, there is of course some changes that will happen in other layers too. Just look at the application layer on top there. So in the application layer, you have things like DHCP, DNS, SMTP. Most of these may need some minor tweaks, minor changes, so they do understand IPv6. So you know that in DHCP, you have DHCP v4 now and DHCP v6. In DNS, latest versions of the DNS software that are being available right now actually already has support for Quad A record, which is the record that maps a domain name to an IPv6 address. But again, largely the changes that will happen will occur in here. All right? So a bit of background, let's look at a bit of history. I've mentioned to you that IPv6 is not exactly so new anymore. It's been around since the 1990s. The earliest recorded discussion about these change to the new version is in 1990, when there was a first wake-up call by a guy named Solinsky on the mailing list about the impending IPv4 address exhaustion. So he mentioned, he did some computation there, and they saw that perhaps if we continue giving the way that we do when we distribute IPv4 addresses, maybe if we do it this way, by 1996, okay, around 96 to 98, they foresaw that we will have run out of IPv4 addresses. How come? Well, IPv4, the entire IPv4 pool consists of how many possible addresses? That's 2 raised to 32. So that is around 4.3 billion addresses. However, not all of it is going to be used. Okay, some of it becomes, of course, your broadcast address, some of it becomes your private addresses, some of them are experimental. So only a chunk of that is, of course, the what we call the public addresses. Another thing is, during the early days of the internet, they didn't foresee that it will become as big as it is today. So how they think that 4.3 billion addresses is enough, okay, which is rightfully right at that point. You have computers, big computers. You don't have things like mobiles, all devices now that are actually using IP. So they saw that 4.3 billion addresses is more than enough. When they give them out, it's given out as classful addresses. Okay, I'm pretty sure some of you have heard the classful addressing before. It just means that your IPv4 addresses are only divided into 3 chunks based on the octets. So you have class A, class B, and class C. Depending on how many addresses you want, you will get either of these 3 classes and nothing in between. Okay, so actually one of the earliest changes they made, one of the temporary changes that they made is to introduce classless addressing to somehow solve the problem of IPv4 address exhaustion. All right, so when they saw that this is going to happen, 2 things came to their mind. One is, of course, to come up with a short-term solution. The short-term solution is, as I've said, classless addressing. You're not confined into these 3 classes anymore. They've introduced CIDR as part of that as well, and VLSM, or the variable length subnet masking. Now, the long-term solution that they started implementing is to find a new protocol, or to come up with a new protocol. So that's what happened here. They formed a group that will discuss this, that will further investigate or how to come up with these new protocols. In 1994, they have the IPNG working group within IETF to manage this effort, and they received a lot of proposals. In 95, that's when one of the recommendations was actually to use 128-bit addresses. So you know by now that IPv6 uses 128 bits in its entire IPv6 address. However, there is really no, well, it has something to do with an agreement between everybody. So the proposal that they came up at that point were to use either 64 bits, to use 128 bits, and maybe some other proposals said to use 64 bits, but flexible addresses, like it can move, something like that. So there, at the end of the day, of course, we know that they agreed to use 128-bit addresses. Okay, now the final specifications for IPv6 was first drafted in 95. So it's RFC 1883, and the current one that we're using right now is RFC 2460, which is the current standard, the very first version of IPv6 protocol specifications. So as you can see, that is in December 1998. And what year is it now? It's 2014, start of 2014. So it's been a long time since we've had it, but the current situation is that we don't have as much people, as much networks that are using IPv6. We still are limited when it comes to these network availabilities, the content availability, as well as people who actually are confident to manage an IPv6 IPv6 network. All right, so any questions so far? Okay, so now let's look at well, why IPv6? Well, it's simple. The main reason is, as we've said, is IPv4 address exhaustion. We are running out of IP addresses. That is due to two things. One is a decreasing supply of IPv4 addresses because it's a limited resource. Another is because of the increasing number of usage. There are, we are in a world right now where we call it the Internet of Things. It's not just one big computer that is in a house or in a laboratory. We have laptops, we have computers, we have mobile devices, even our equipment. Maybe some of our home appliances would be using IP in the near future. Well, some of them already do. So there is really a need to come up with a new protocol that can give you this larger pool. The global pool has been, for IPv4, has been officially exhausted in 2000 and I think around 2011, right? So what does that mean? So there is a hierarchy of distribution of IP addresses. It comes from IANA. So if you've never heard of IANA, IANA is the Internet Assigned Numbers Authority. So from IANA, they distribute these number resources to the regional internet registries. We have 5 regional internet registries, one for each region in the world. So we have one for Northern America and Canada, so that is ARIN. You have LACNIC for Latin America and the Caribbean. You have RIPE NCC for Europe and Middle East. You have APNIC for the African region. And of course, in our region, in the Asia Pacific, we have APNIC. So they distribute that to all these 5 RIRs. So at that point, they gave out all the 5 last /8 to the 5 RIRs. And so now, with IANA, we no longer have any IPv4 addresses. Okay, so they've already assigned it. Now in our region, in APNIC region, we also have already started giving from that final /8 pool. So what is the implication of that? Before the final /8 policy, you can request more than a /22 IPv4 block as long as you can justify that you need it. Now, when they've implemented that, when we enter that official final /8, we are only giving a maximum of a /22. So you can request /24 to a /22 IPv4 addresses only. So it's only enough for new ISPs or new entrants into the industry who wants to get started. But if you are in a big ISP, probably that is, of course, not enough. So /22 is just how many addresses, right? It's really not enough for you. So IPv6 answers all those questions. It provides you with a much larger IP address space. We have mentioned that IPv4 has 32 bits in its address, which gives us a maximum of 4.3 billion possible addresses. With IPv6, we are using 128 bits. So from 32, the address is increased by 4. But the actual address, of course, the number of addresses is not just multiplied by 4. It is an exponent. So it is 2 raised to 128, which gives us around 3.4 times 10 to the 38 possible addressable devices. Okay, which is good news for us. Okay, that is really a lot. Now, another thing with IPv6 is, of course, when they're coming up with a new protocol, when they came up with IPv4 first, that was in late 1970s. If you look at the TCP/IP protocol specifications, that was it was published by Bob Kahn and there's another guy, Vint Cerf. So those two guys, they came up with the TCP/IP protocol. Now, we don't really have as much experience using IP or using internet yet at that time. So when they came up with IPv6 in 1990s, they saw the good and the bad side of using IPv4 and they tried to improve it. So there are also new things that are introduced, new functionalities and improvements that are introduced with IPv6, which is what we're going to look next. So it's this one. First, well, you're already very familiar with the first one there. It's an increase from 32 bits to 128 bits. So let's just skip that. Next is stateless auto-configuration. So that is something new. Stateless auto-configuration means that there's no need for you to configure IP address anymore on your systems. You let your machines do the job. So in IPv4, how do you assign IP address? In the early days, it is to assign them manually, okay, which is what you do on servers or equipment that needs static address. And you also can assign dynamic addresses to maybe mostly to end hosts. Now, stateless auto-configuration is something similar. It's a bit close to DHCP, but it's not exactly DHCP in a sense. When you say stateless auto-configuration, your machine, the moment that you enable IPv6 in it, you can now have an IPv6 address. It starts with FE80. It's what we call it as a link local address. So with that, you are now able to connect to all the machines within the same network without any configuration required on your end. Okay, so that is actually a good thing, because in IPv6 it's hard to assign address, especially if you're using static because of the length of the actual IPv6 address. Okay, so stateless auto-configuration is a very good thing, especially when you're just starting to use IPv6. Next is it uses fixed header size, which is 40 bytes, compared to 20 bytes of IPv4. We will look at that more closely later on as we see the actual headers and what are the different header fields. Now, suffice it to say at this point that when we talk about fixed header size, it can result to having better router or switch or any equipment, better performance with that. Why is that? Because your router does not have to spend some time, even if it's just like a few nanoseconds. But if he has to do it per packet and he receives millions of packets every time, then it adds up. So fixed header size can eliminate that extra time that it takes for your router, for your equipment to do these checks and to do these calculations. It is 64-bit aligned. Nowadays, most equipment already uses 64-bit, so probably that's not really very relevant anymore. But in the early days where we have both 32 bits and 64 bits, then that actually results to a lot of better performance for your routers. Next is no hop-by-hop segmentation. So has any of you heard of, or does anyone understand what is path MTU discovery? Okay, or what is MTU? MTU is maximum transmission unit. So that is, think of it as the size of the packets that is allowed going through certain links. When you transfer, let's say you're transferring your data or a packet from point A to point C, and it has to go through point B. So when it passes through the links there, point A to point B, what is the maximum that is allowed? Usually it is set to MTU size of 1500. Okay, that's usually what we set. So 1500 for that, and then B to C probably 1500, or you can customize it. You can have your own way. Now, if let's say from A to B, it only allows 1200. But you're sending a packet that is 1500 in size. So what happens there? It will be dropped and you will have to fragment and resend them separately. That's what you do. In IPv6, when we say no hop-by-hop segmentation, we mean that it tries to find out the maximum MTU size before actually sending the packet. Alright, so given the same example that we're just looking at, if the size is 1200, before actually sending the packet, the router already knows, router A already knows that the maximum would be 1200, and therefore he will only create the packet with that size and nothing bigger than that. So you eliminate the extra effort, extra time that it takes for your packet to be sent from A to B and then be dropped and resent again. So that is a good thing. That makes things a bit faster. Okay, next is built-in features for multicast and anycast groups. You can say that it's also very much related to this last one, which is no more broadcast. In IPv6, we don't use broadcast. Broadcast is a good thing. However, broadcast is also being used in a lot of malicious things. So it adds to the noise. When you say broadcast, what does that mean? If I'm a router, I'm looking for another router, I would just go into a room and shout, like, which is this router? I'm looking for a router with address 192.168.1.20, something like that, right? So you're sending broadcast messages to everyone and not just to a selected few. So they don't want that in IPv6, so they decided to eliminate it. Instead, we are using multicast. Multicast and anycast, we have that in IPv4 as well. So the functions are pretty much the same. So if you have, or if you want to send to a certain group, maybe you're broadcasting to just all the routers, then you have a separate multicast group for that, and separate multicast groups as well for different routing protocols. It eliminates triangular routing. We'll not look very closely to that, but essentially, when you say triangular routing, it's like when you need to send, say you're roaming, okay? When you need to send data, with triangular routing, all of your data will have to go through your home network first before the network that you're actually corresponding with. So it's a bit laggy because you have 3 points to always connect to. So in IPv6, this is a work in progress, all right? They try to make things easier, make it possible for, let's say, your network or your device to communicate directly to your corresponding network without having to go through binding updates with your home network. Okay, so maybe you'll do that just once, but all the conversations after the initial binding would be from your network going to the corresponding network, and nothing goes through your home network anymore. Okay, now it also has built-in support for IPsec, VPN, and QoS tagging, which is very, very nice. Now, one common thing that you would probably hear is that people would say that IPv6 is much more secure. IPv6 is more secure because of this, because of IPsec. Okay, IPsec is IP security. We have IPsec in IPv4, but IPsec was originally designed or created to be part of the IPv6 protocol. It's only because it's been a while, it's taking a while for us to migrate to IPv6. That's why they ported this IPsec protocol to work hand in hand or to work alongside IPv4. So it is a separate protocol in IPv4. But in IPv6, the idea is, the goal is to have these IPsec capabilities as part of the IPv6 protocol itself. All right. What else? It's got VPN, it's got QoS tagging, everything that has to do with securing your IPv6 network. But again, it doesn't mean that if you're running an IPv6 network, it's already secure, all of it, but because it's still part of all the TCP/IP layers. You still have to protect all the other layers, not just your IP layer. All right? So these are just some of the things, some of the new things that are being introduced as part of IPv6. Any questions? No questions? All right. Now let's move on and look at the different IPv6 addressing models. So the best way, or if you want to have a more detailed discussion on this, that is in RFC 4291. Now, for those of you who are familiar with the addressing model in IPv4, it's essentially the same, except that it doesn't have broadcast. In IPv4, you have unicast, anycast, multicast, and broadcast. in IPv6, we just don't have broadcast. So let's just define each of them very quickly. Unicast, from its name itself, it is the communications process there is from one interface to another interface. A single interface, you have a source address going to another unicast destination address. So you have 1:1 correspondence between your two endpoints. So the next one is Anycast, and it's very closely related to multicast. So I think I'll discuss multicast first. Multicast is when you send out a packet. Say you formulate your packet, you have a source address. Your source address is your interface's logical address, of course. So that is a unicast address. However, your destination address will be a multicast address. So this is an address assigned not just to one interface, not just to one host or one machine. It is assigned to multiple machines. So in this example, as you can see, we have 3 computers that are using the same multicast address. What happens when, let's say, this source host sends a packet to the multicast address? It will be sent through to all of these multicast addresses. Okay, so it's like you have a group, a multicast group, and then everybody will be able to receive it. A common analogy that I use for this is when, let's say, I am sending to a mailing list. Okay, I'm part of a mailing list and I'm sending to them. I only have to create my email once, right? And then send it to that address, and everybody that belongs to that address receives it. Okay, it's simple. So you don't have to create different packets for these different devices. It's just one. So easier work for your machines there. Where do we use it? A lot of video streaming, webcasting type of functions and applications uses multicast, and some audio and video video conferencing tools as well. Anycast is similar to multicast, except that when you send to an Anycast address, it will only be received by one machine, one interface. So all of these machines belong to the same Anycast group. They have the same Anycast address. However, only the one that is closest to my sending host will be able to receive my packet. Okay, how do we know which is the closest? Well, we will leave the routing protocols to decide on that. Alright, so those are the 3 addressing models. The reason we're discussing this is it is very important to know how these functions at the same time. It is, for starters, if you don't understand the difference between this, it will be hard for us to look at the different groups of IPv6 addresses. When you look at that in the later slides or in the next module, you'll see that we discuss a lot of unicast addresses, but some IPv6 addresses are used for other purposes as well, such as multicast. And as an example, when you do neighbor discovery in IPv4, when you want to find another machine, what do? You send an ARP request, right? You send an ARP request, you expect an ARP reply. How does it work, or where does it work? It uses broadcasts. Okay, it sends out a broadcast message to everyone. Now in IPv6, we don't have broadcast anymore. So when we do something like that discovery process, we use multicast. And we will be using multicast addresses for that. Alright? Okay, now these are, what you can see in this diagram is the headers. The header is something that is processed by your routers in order for your packet to be transferred between routers until, of course, it reaches the very end. It reaches its intended destination. Okay, so these are what you can consider as control signals, control information that are used to manage the processing and the routing of your data, of your datagram. Okay, so you can see that there there's a bit of a change from IPv4 header to IPv6. IPv6 is a little bigger. Okay, it's not to scale, but you can notice that some of the fields there are bigger, of course. But you can also see that some of them have been removed. So there you have a simpler IPv6 header. So let's look at this. There's a color coding scheme here. The ones that are in yellow, I'm not sure if you can see it as yellow from your end, something like a bit of orange as well. Okay, someone raised his hand. Will you please write your question on the chat? Because if I allow this, the audio will be transferred to you. So I suggest that if you have any questions or you have anything to add, can you please write them down on the chat panel? Okay? So anyway, going back here, the ones in yellow or a bit of orange for some of you perhaps is some things that are kept from IPv4 to IPv6. So what are they? Version in IPv4, you still have a version field in IPv6. In IPv4, of course, the content there will be 010044. In IPv6, it will be 011046. Your source and destination addresses will still be the same. You have source address will be 32 bits for IPv4, destination address is 32 bits. So in IPv6, you just have a bigger field because you have to accommodate 128 bits for each. So that's why you just make it bigger so you can see the difference between them. But everything else is still the same. All right? Now, how about the red ones? Red means fields that have not been kept in IPv6, meaning we eliminated them or we moved them somewhere else. Okay, so you have here the header length. We won't be using header length anymore. Why is that? Because in IPv6 we have fixed header. We have fixed header size, so we just need the payload length. So it's actually this one. We have payload length here. We have identification, flags, fragmentation, offsets have been removed. Why? We have a different fragment extension headers. So let's just clarify something here. The reason we remove a lot of these things is partly because some cases when you send a packet, it's not actually used. Okay, in some cases it is used. So the idea is you don't want your router to process something if the contents are just all zeros or if it doesn't mean anything for that particular packet, right? So what they did was remove it here, and then we will just add them later on when we need it. Okay, so it's not there by default, but it will be added when necessary. We call this extension headers. It's something new in IPv6. Okay, so again, those red ones are now being removed, options fields, paddings, and everything. We don't want that in IPv6. Next, we have the bluish green color there, the ones that have been still kept in IPv6, but there are a few changes. So type of service is now traffic class in IPv6. Total length, this is what I've been discussing earlier. Total length has got to do with header length plus the payload length. We don't need the header length anymore in v6, so you only have your payload length. Okay, what else? Time to live in IPv4. Time to live is a measure of time, right? It's in seconds, it's in nanoseconds. How much time do you have for your packet to get to its destination interface? However, in IPv6, they decided not to use time because of its sensitivity. Because even though you're maybe using, let's say, an external source of time for both of your machines, there is a likelihood that there are minute differences between these times. So what they did was use hop limits instead. So the number of hops before your packet will be dropped if it doesn't get to its destination. Okay? What else? Next header is a new thing. We said that we've eliminated a lot of things here and we will add them onto what we call an extension header. So we have the next header field to point to us what the next header will be. So is the next header an extension header? If so, is it a fragmentation header, an options header, maybe an IPsec header, things like that? Or is it your TCP header, which means that what follows is already your payload and nothing else? Okay, so that's the purpose of your next header fields. Now there's another one here, a new field that has been introduced in IPv6, which is what we call as flow label. So in v4 and v6, we already have type of service or traffic class. So it sort of gives us a way of classifying the data that we're receiving and giving priority to them. However, flow label is something similar to that, but it gives us more control. It allows us to have or to define different flows. And from that, we can define priority for those specific flows. For example, you have data, you have voice, maybe you have streaming or video. So which ones do you prioritize next? If you want to prioritize video and also maybe voice, then you create a flow for each of them and then assign priority as necessary. Okay, so just to recap what we've discussed for this one, in IPv4, how many headers do we have? We have 10 basic header fields. IPv6 is a lot simpler. We have 6 basic header fields. In IPv6, we're using 40 bytes or 40 octets, but it is fixed size. In IPv4, we have 20 octets or 20 bytes, but that is the minimum. If you add a lot of things on your options field and everywhere else, it has a tendency to grow bigger. So every time your machine, your router will have to process and compute the size of your packet itself. In IPv6, we don't have that because again, we're using fixed 40 octet as our header size. Okay, so in the end, we have a smaller number of header fields. It's also 64-bit aligned, and so this justifies our claim earlier that we can process IPv6 headers a lot faster because of this. Okay, any questions? All right. Okay, now as I've said, we'll just look at IPv6 addresses very, well, not in very detail, just the basic ones, because we have another module which actually is for the next one that discusses the IPv6 addresses. But I think it's essential if you're just attending this class. Now, IPv6 addresses, we've said that we're using 128 bits. Okay, but how do we actually write them down? In IPv4, how do you write down an IPv4 address? We use what we call the dotted decimal representation or dotted decimal format. What does that mean? We have 32 bits, we divide that into octets, so we have 4 fields, and each of them is separated by a dot, and each octet is converted into decimal. So you can have things like 192.168.1.100 or 172.16.20.4, something like that. In IPv6, we are not using decimals. Okay, in IPv6, we are using hexadecimals, which is a value from based on 4 bits or what we call as nibbles. Okay, and each of that will have values from 0000 to 1111. So that's 0 all the way up to F. Okay, so you will see letters in an IPv6 address. It's not just numbers, but again, it's just up to F, which is our entire range for our hexadecimal digits. So how do you write them down? From 128 bits, if we're using hexadecimals, that means we have somehow trimmed it down to 32, right? 32 hexadecimal digits. But we can still trim it down. We group them into fours, okay? So each of that is a field, and each of the field is separated by a colon. So this is a complete example. If you try to count the number of fields and count the number of hexadecimal digits, it should be correct. It should have how many hexadecimal digits? 32. And how many fields? 8 fields. Each of the field is separated by a colon. Okay? Now, you will see that when you have started deploying IPv6 in your own networks, you will be using the very first blocks. Maybe from your /32, you will be using the first /64, which has a lot of zeros. So there are ways in which we can trim it down. Your machines will do that automatically for you. But just so you understand, this is what happens there. So let's say, for example, that you have this address. Okay, so 2001 db8 colon 0, all zeros there, 036E1250 So you'll see a lot of zeros somewhere in between there. You can actually remove that. You can trim it down. One is if you have leading zeros. So in here you have 4 zeros there. The first 3 are leading zeros, so you can just write them down as 0. If you have 036E here, you can trim that down, remove the first 0, you have 36E. Now, another thing is you can use null values. So you have 3 fields here that are adjacent to each other, and they are all zeros. So what can you do? You can just remove all of that and replace it with a double colon. So IPv6 is kind of known for that double colon symbol. So you have this address. You can easily know that this one actually represents 3 fields because this entire thing must have 8. Okay, so that is your IPv6 address there. Now, IPv6 addressing structure. In IPv4, we have something like network bits and host bits. So if you want to compare that in v4, you can think of it in that way. But the way they work is a bit different, of course. Now, in IPv6, you subdivide your address into 2 parts. You have your network prefix and you have your interface ID. Your interface ID is what you use to assign to your hosts. Okay? Your network prefix is what you use to do your subnetting. Okay, so let's look at the way that we delegate IPv6 addresses. Where does it start? It starts from IANA, as I've said. From IANA, they distribute /12 IPv6 blocks to the RIRs. Now, from the RIR, you request your IPv6 block. Normally, the maximum that you will get if you are a service provider, a local internet registry, is a /32 IPv6 block. So it's somewhere around this line, right? So you have /32. Now, from that /32, now you're an ISP, you have customers. These customers can either be insights, can either be a big multinational company perhaps, or it can even be another smaller ISP. So you give their IPv6 blocks accordingly. So you have the option to give somewhere from here up to /64. Nothing smaller than that. Okay, so you only have this line from /32 to /64 to distribute to your customers. Again, why is that? Because this last part is what you use to assign to your hosts. So each host, actually, if you have, let's say, a network, a room, one subnet, maybe you have 5 computers there, maybe you have 100, maybe you have 1,000. It doesn't matter. You have to assign a single /64 IPv6 block to that. Okay, and that is a limitation that we have at the moment. Okay, if you try to assign, let's say, to most operating systems would not understand or will not be able to interpret properly an IPv6 address that has a prefix that is smaller than a /64. But if you're going to do it, and let's say things like routers, then that's not a problem. But let's say on your Windows machine, automatically it becomes a /64 block. All right, so going back to this, you're an ISP, you're giving to your customers different IPv6 blocks. You can give a /64 if the customer is a very small, maybe it's a home user. You can give a /64 if you're not expecting them to grow. Okay, but if it's a very, maybe there's a chance that they will need more than one subnet in the future, then you'll have to give more than that. So small size or medium size companies normally get a /48. Okay, something smaller than that is probably /56. Why /56? It's because it's a good well, it's a midpoint between your /48 and your /64. So when you distribute addresses, you will learn this when you go into address planning. If you want to have a look at that later on, you learn that it's easier to distribute addresses per nibble. Okay, so per factor of 4. Okay, just to avoid that human factor, human error. Okay, so this is a very important slide because it helps you understand how you will plan to distribute your IPv6 address blocks to your customers. Okay, any questions on this? Just a little bit about the interface ID. So where is the interface ID? It's this last 64 bits. How do we assign that? So lower 64 bits is assigned either these ways. One is, well, similar to IPv4, you can always manually configure them. Similar to IPv4 again, you can use DHCP. This time around, it's what we call as DHCP version 6. Okay? The difference, by the way, with DHCP version 4 and 6 is mostly with assigning the address. When you assign a DHCP address in IPv4, you give an actual IPv4 address to the interface. In IPv6, you provide the network prefix and you let the machine come up with its interface ID part. Okay, so the interface ID can be generated by your operating system, by your machine, either using a pseudo-random number, which is this one, or using EUI64, or more specifically, it's a modified EUI64. It is based on the machine's MAC address. So see here, probably don't have that. I don't have that slide, but basically, based on your 48-bit MAC address, you create, or the machine will create, the 64-bit EUI64. So what's the implication for that? For those who are a bit concerned about security, they saw that maybe that's not a very good thing. Why? Because, well, let's say I'm connected to APNIC right now. Okay, my machine is connected to APNIC. My MAC address is a physical address. It is unique to my machine. Okay, everywhere around the world it is unique. So that means if I change networks, maybe tomorrow I'm gonna go somewhere else, maybe in another country, and then I will connect to the IPv6 network and I will have a new IPv6 address, but the last part, the interface ID part, will remain the same, again because it's based on my MAC address. So that's some people find it as a security issue. That's why they have pseudo-random numbers. Most of the latest operating systems like Windows machines, also the latest versions of Mac OS X, uses pseudo-random numbers by default, but you can always switch back to EUI64 if you choose to do that. Okay, any questions? These are the prefix that we're using globally, meaning these are the public addresses. So it is this range 2000:/3. So what happened again is from Ayana, we've distributed /12s to the RARs. So you can see these are the 5 RARs. Each of them has a /12. So maybe when you request for your IPv6 addresses from APNIC, you will probably get them from this block. So 2400/12. So you can see how big the IPv6 address just by looking at this. 200/3. So how many /12s can you get from a /3? Okay, that's already a lot. So that is 2 raised to 9, which is 512/12s. When these RARs run out of IPv6, which is very far from happening at this point, then all they need to do is come back to IANA and request for another /12. There are 506/12s left within IANA, right? So this is a good diagram that shows that. This is your /3. Okay, from that we have 512/12s. 5 of them have been given to the RIRs. 1 of them have been used for other things, miscellaneous experimental purposes. And so we have still 506/12s within IANA. Let's just say in 20 years' time, we've used up all these /3 public address blocks, then we can always get another /3, another piece of the pie in the entire IPv6 address space. So you can imagine how big the IPv6 address space is just by looking at this diagram. So at this point, I would just like to encourage everybody. I'm not sure if most of you already have IPv6 blocks, but if you don't, I think it's the best time to do it. Requesting for IPv6 is never as easy as it is over the past few years. You can, if you are an APNIC member, you can already request for your IPv6 address. We have this program called the Kickstart IPv6 program, where you can request or you can apply for membership and also request for your v4 and v6 addresses all at the same time. Or you can also get your IPv6 blocks right away if you already are an APNIC member. So essentially, all you need to do is claim your IPv6 address by logging in to My APNIC, and then there's a link there somewhere in the main landing page that tells you to to get those or to claim those IPv6 address. So what we call that as the one-click policy. So by default, if you have an allocation of IPv4, you are entitled to get a /32 IPv6 block. If you have an assignment of IPv4, then you can get a /48 IPv6 block. All right, so it's really that easy, and you can start by requesting them and playing around with it. Maybe set up an environment, a laboratory where you can try and assign and configure maybe your routing protocols to use IPv6 and things like that. Okay, so this is the IPv6 BGP routing table. For those of you who are familiar, in IPv4 we have a lot more than this. But it's very good to note that starting from this, which is early 2000, up to what we have now, which is early 2014. I might have moved something here. Hang on. There we go. So you can see that what we have now, I got this statistics in mid-December. So we have around 16,000 BGP entries in IPv6. So if you compare that again with IPv4, it's still a lot less. But the good news is it is going up. And it's very steep, meaning that a lot of networks are now starting to deploy IPv6 and are announcing their IPv6 blocks to the global routing table. Okay? So I think that's where we will end this class. I'd like to know if you have any questions. If you do, can you please write them down on the chat? While you're doing that, while you're thinking of questions or things to add, I'll just also post the link to the survey. It's there on the slides, but it's easier if you can just put them down, write them down on the chat as well, so you only have to click it. So this one. So this is the link to the survey. If you can, please take some time to answer the survey. And if you want a copy of the slides, it will be available to you once you've completed the survey. Now, throughout the day, we will still be covering a lot of things about IPv6. So please do join us. We have IPv6 addressing and subnetting, transition, and also address planning. All of them are 1 hour intervals. If you haven't registered for that, you can always use the same credentials that you used to log into this. Okay, anyway, thank you very much, everybody. If you don't have any questions now, I'd like to take this opportunity to thank everyone for the time and also for your attention and also your feedback. So I hope to see you again in another e-learning class. Bye-bye.